Welcome back. Let us continue our discussion on the cascode amplifier, and we are going to look into the folded cascode configuration, which can help us in achieving better signal swing at the input node and also facilitate better biasing for the overall amplifier. So, the basic operation involved in the folded cascode is you can start with the ideal current source, where our input device is the NMOS, and you are having the cascode operation being provided by a PMOS device, and then you have another NMOS load. This is a single ended cascode. We will be looking into the differential version of that also, but it is important to look at the functionality here. Once we are comfortable with this, we can go for the differential version. So, here you have some input signal, which is some gate bias plus the AC signal V in, and we are looking at the output voltage over here, V out, and we need to look at the overall signal gain from here to here. What is happening in the overall signal propagation from the input point to the output point. These are again some gate bias voltages. If I call this M1, this is maybe M2, M3 and M4 with certain gate bias voltages. And now, if I look at the overall operation, if I assume that this is a DC bias current and which is an ideal current, the small signal current provided by M1, which is GM1 V in, right. This is the small signal current provided by M1 if you are applying an AC signal at the gate of M1. If this is an ideal current source, the small signal impedance of the IDC is very large, infinite ideally, and therefore, this entire small signal current will be flowing into this direction, right. So, this entire GM1 times V in flows here, because for the AC analysis, this ideal current source is going to be open circuit. It is not going to have any small signal current flowing. As a result, this entire GM1 V in goes in. What is M2 doing over here? If I forget about the first part of the circuit, M2 is acting like a common gate circuit, where the input signal is at the source, gate is at the AC ground at a potential, fixed potential, and therefore, whatever small signal current flows into the source of M2 will be injected at the drain of M2, and whatever impedance it sees over here at the drain, that current will be multiplied by that impedance and give you a voltage. That is what we have studied for the cascode stage. So, if I look at the situation of M2, it is having some small signal resistance connected in the drain. What is that impedance? This is M2 with gate AC ground. You are having some signal which is GM1 times V in, and it is having a large impedance given by the impedance looking into the drain of M3, which is GM3 RO3 times RO4, right. So, impedance looking into the drain of cascode device is going to be GM3 RO3 times RO4, and as a result, whatever signal comes in over here. So, if I draw the directions correctly, the GM1 V in is from the drain to source. So, the GM1 V in direction is this, and as a result, the same current, whatever current enters into the source of M3 should be coming out of the drain of M3, and as a result, this current will be getting multiplied by this factor. One factor that I missed was the RO of the M1 itself. So, you know that you also have a RO of M1 over here, right, and looking into the direction of the source of M2, what is the impedance? RO we have discussed, right. So, that will be given by this large impedance GM3 RO3 RO4 divided by GM2 RO2. So, the impedance looking into the source is equal to the drain impedance divided by the intrinsic gain, which is GM2 RO2. So, this is going to be of the order of RO. So, the impedance looking into the source of M2 is also RO, and for this M1, therefore, the scenario is that the M1 itself is having its small signal RO from drain to AC ground, because the RO appears between drain and AC ground, drain and source is at AC ground, and the DC current is anyway open. So, it does not give you the ideal. So, this does not give you any impedance, that is infinite, and then you are having the overall impedance looking into the source of M2, which is also RO. So, whatever GM VGS is produced by this MOSFET, half of that only goes into the RO, which is looking into the source of M2. Therefore, I have this 0.5 factor coming over here, and as a result the V out can be given as minus 0.5 GM 1 V in times this GM 3 RO 3 RO 4, and of course, we are having an overall gain of 1 upon 2 GM RO square. This is your gain. So, this is again giving us the same functionality, same behavior as our normal stacked cascode amplifier that we saw. Only difference is that we have applied input signal to the gate of NMOS, and rather than sending the current into the stack of cascode of NMOS and a stacked PMOS load, we have folded the current. The small signal current has been folded down, and now it is going to the stack of the NMOS cascode load and a PMOS cascode device. This is a cascode transistor, this is a PMOS cascode device, and you are having a cascode load. So, the small signal current has been folded down, and therefore, we term this as a folded cascode. And of course, we can look at the overall DC potential over here. Now, if I replace this by a non-ideal current source, then we can talk about the DC biasing point over here and the signal swing over here. So, let us replace this by a non-ideal current source, and then look at the modified gain and then the signal swing at the output point and the input point. So, what is the difference in this signal analysis if I replace it by a non-ideal current source realized with the help of just a simple PMOS transistor supposed to supply some fixed current. So, I can realize it with the help of a PMOS transistor, and this is in turn biased with some reference branch that we can construct, right. So, is there any difference we are going to encounter in the resulting small signal analysis? What stage we are going to have the difference? So, we can see that this is going to give you another impedance RO3, RO whatever number is. So, here you have an RO looking into the drain of this PMOS, and now you have another RO over here and RO of the M1 also. Therefore, only 1/3 of that small signal current goes out, and therefore, you are going to have 1/3 factor coming over here. So, this basically gives us the overall modified gain because of the folded cascode with a non-ideal current source. Now, once we have this, we can also look at the other factors like the signal swing, DC bias conditions and all. So, let us do that in a fresh diagram. Any question before we proceed and look at the DC biasing, signal swing? Bandwidth point of view or frequency response point of view, again we have similar scenario. Even if we have this configuration, the overall amplifier is going to have this one as the critical or the high impedance node, because if you look at the impedance over here, once again it is going to be the impedance looking upward, R up parallel R down. R down is still GM RO square, GM times RO square. R up, what is R up? So, only difference is that in the source of M2, rather than having RO, now you have RO by 2, and therefore, the impedance will be GM RO of M2 times RO by 2. Order is similar, GM RO square by 2. So, therefore, you are going to have similar magnitude of the small signal resistance over here, and hence the pole magnitude also remains similar, and the other points you still have impedances given by close to RO by 2. So, at this point you have RO of this MOSFET, RO here, and the RO of the PMOS M2. As a result, you are having RO by 3 over here. Here also you are having similar values. So, at these 2 points, once again you have non-dominant poles, and the output point you have the dominant pole. So, from the point of view of frequency response, the behavior remains more or less similar. This is clear, the small signal analysis and frequency response. Any question before we look into the signal swing once again?
Sir, here we need the gain voltage of first NMOS also is defined, otherwise.
Sorry?
Voltage of first NMOS.
Drain voltage. Yes, so
because it is going to PMOS source, so how means it, if it is small, then there will be problem.
no, that has to be defined properly. So, of course, it has to be sufficiently high so that we are able to directly connect it to the PMOS source. Any other question? So we'll see that how are we going to do that. So let us look at the signal swing with the real current source that we have. I'm not discussing how we are biasing this source. Suppose it is biased appropriately, and at the input side you are having the. It will be prudent to directly go to the differential topology. So rather than going for the DC analysis here, since we are going to ultimately deal with the DC analysis of our differential scheme, so let us go for the differential topology right ahead, because all the DC biasing and the signal swing analysis that we have to do, ultimately it is more meaningful to do it for the differential scheme, because we do not use this kind of single ended amplifiers anywhere in our circuits, integrated circuits. So let us apply the same scheme for the differential operation and apply at the arrive at the folded cascode differential amplifier. So if I do that, I can as I just mentioned here, I can implement this current source using the PMOS transistor over here, and the stack remains as it is. Only thing is it will be differential. You have the two pairs coming in. So let us do that. So for the time being, I am not discussing how these fields will be biased. I will arrive at that very soon. So this is the overall differential scheme that you have. Assume that these are appropriate DC biases, and this is again tail current source for the differential pair. And if I look at the similarity between the single ended one and the corresponding differential topology, once again, if I look at the differential half circuit, so this becomes AC ground. As a result, this is your M1. The current source over here is being realized with the help of the PMOS over here, and then you have the other PMOS and 2 NMOS in stack coming over here. So the differential half circuit will be exactly same as what we just discussed. Is it clear? No issues with the translation to the the differential topology. Now right now I am drawing it as a fully differential topology. I can also convert it into a differential to single ended version. So we will look at the two schemes. So far we have been discussing the fully differential topologies. Let us stick to the differential one, and then we will also discuss briefly the single ended output one. So in those cases, how does the signal swing etc. change, or how does the biasing scheme change? So that we will discuss briefly, but let us stick to the fully differential. So here once again the output points are over here, and we can look at the output common mode level that is required for maximum symmetric swing. So this is now symmetric on the upper side and the lower side. So the stack is symmetric for PMOS and NMOS. So you don't have a tail current source over here, and therefore as per our earlier analysis, we can conclude that the maximum and minimum output voltage that you can have is going to be VDD minus 2V overdrive on this side. Lower side you can have 2V overdrive, and therefore the V out max is VDD minus 2V overdrive. You can call it V overdrive P, assuming it to be close to V overdrive of N also, and V out min is 2V overdrive. And again, if you want to verify, you can just trace from the bottommost level. So the voltage over here is going to be the VGS of the MOSFET. So if I say call this the M1, M2, let me call this 1. So both together are 1, and this is together 2, 3, 4 and 5. This one 6. So I am just numbering the pairs. So here if I look at the bottommost level, so you are having some VGS2. VGS2, the minimum allowed potential at the drain that you can have, VD2 min is VGS2 minus VT2, and corresponding to that you have a minimum allowed gate voltage at G3. So VG3 min is equal to VD2 min plus VGS3, and as a result the output V out min is going to be VG3 min minus VT3, and hence this is nothing else but VGS2 minus VT2 plus VGS3 minus VT3, hence this is equal to 2V overdrive. This is the best you can have, minimum allowed potential, provided the VG3 is also equal to VG3 min, and the source potential of M2 is also equal to the VD2 min. If you achieve that, then you can have the maximum minimum allowed potential at the output equal to 2 V overdrive. And likewise, on the upper side you can have VDD minus 2 V overdrive. You can verify that by tracking it from the topmost level coming to this point. So, for a given VG5 you will have VG plus mod VT, corresponding with that the maximum value we can have over here is VG minus plus mod VTP minus VSG, again minus VSG plus mod VTP. So, again you will get the same expression. So, from the output side we have this particular scheme, and we are trying to go to we are going to have a bias which is going to help us in achieving this maximum and minimum voltage level. That is one target for this design. And now we can also look at the input side. So, input side, this is similar to our differential amplifier with current source load. So, you are having input pair, and the drain side is connected to PMOS, and therefore, the limitation on the input common mode range or the input signal level is input common mode level is mitigated, because here the output DC point can be pretty high. The maximum value that you can have over here is VGP plus mod VTP. In order to get maximum possible swing at this node, you would like to push this DC point to maximum possible value, which is going to be VG5 5 plus mod VTP, right. And as a result, the maximum value that you can have over here is going to be VG5 plus mod VTP plus mod VTP, which can be pretty large. And as a result, the limitation on input common mode range on the upper side that we had in the original design, in the original example, it has been mitigated. It can go to a much larger value. Lower side you have similar case. So, lower side you can go to the minimum value that you can have is VG minus VT plus VGS. So, lower side similar, but severe constraint was coming on the upper side, because you had 3 stacks on the top of that. That has been mitigated. Now, I can go to a much larger value on the upper side. So, as a result, I can have a feedback operation where the input common mode range can vary a lot, and if you are having if you are, for example, going for the direct DC biasing of the input from the output, that is also very much feasible over here, because even if you put this VDD by 2, it's not going to be severely, it's very much acceptable. Even if you're having a VDD by 2 over here, it is not severely affecting my output common mode range, right. So, the input DC level is not directly linked to the output common mode value, or the output DC point, or the output range. So, these two are getting decoupled. So, VDD by 2 over here does not necessarily have any influence on the DC point here. In the previous case, we saw that if you are putting a DC point VDD by, if you are trying to put a VDD by 2 over here, 1 volt over here, then it was violating my minimum allowed voltage level over here, which was 0.6 volt. But here that is not the case. I can have a input DC point which is not conflicting with my output common mode level. So, now the next question is looking at the overall signal, overall biasing scheme for the differential operation, and looking at the biasing for the input side as well, looking at the biasing of these individual mirrors. So, for that we need to look at the biasing scheme which can help us in generating minimum allowed potential for the gate voltage of the M3 for a given biasing point for the gate voltage of M2. So, we have discussed one simpler scheme. What we have seen here is that, okay, one of the very simplest scheme can be to use a cascode mirror. Just like we do it for a simple current mirror, we can use a cascode mirror, and you can put a reference current in the cascode branch, and that is going to develop a VGS over here, another VGS over here, sorry, VGS over here, and that is going to provide the right VGS for these two MOSFETs. That is basically our simple cascode mirror, where one side you are having a stacked diode connected transistor, and that is giving you an appropriate value of VGS to bias these two transistors. So, I can imagine that, okay, I have a reference current getting injected into a diode connected branch like this, and I have the gate voltage is developed over here. I can put it over here. I can bias the stack of the NMOS using this scheme. Likewise, for the PMOS, I can have a similar DC bias, and you have a PMOS diode current, or sorry, a PMOS cascode current mirror, and with the help of that, I can generate the bias points over here. That is very much possible. But here we have also seen that this particular scheme does not give me the minimum allowed DC potential over here, because this is if this is VGS, the DC point over here is also VGS, and as a result the DC potential at the gate of this MOSFET you are getting is 2 VGS, and the minimum allowed DC potential that we had was VGS minus VT plus VGS. So, it is basically 2 VGS minus VT, but now it is 2 VGS, and therefore, the minimum allowed potential here can be 2 VGS minus VT. So, here the V out min in this case, if I use this kind of biasing, it can be at the max, at the min 2 VGS minus VT, which is basically 2 V overdrive plus VT, because V overdrive is basically VGS minus VT. So, I have VT higher, the V out min is larger by VT, and VT can be pretty significant 0.3, 0.4 volt, and hence the V out min has been increased by that value. Therefore, this is definitely not the best case. I need to look for alternate schemes where I can intentionally force this node to the minimum possible value, which is going to be Vg minus Vt. So, this is in this particular configuration, what is this particular potential I can expect? If this is 2 VGS and you are having same current in these two branches, I would expect this potential to be close to VGS minus VGS. So, there is also VGS. So, it is not really the minimum value, which is VGS minus Vt. This is VGS, this is also VGS. So, this is unnecessary wasting some voltage headroom. I can afford a significantly smaller voltage over here. Right now, it is VGS because of the stacked MOSFET 2 PMOS diode connections. This is VGS, this is VGS. As a result, this 2 VGS, and as a result, if these two are matched, if they are identical, having the same current, this will also have gate potential minus VGS, and therefore, this is going to be same as VGS. Whereas, the minimum potential that I can have here is VGS minus VT. So, I would like to have a biasing scheme which can let me have that minimum allowed potential, which is VG minus VT. So, let us see one possible scheme to do that. You call this say M1, M2, 3, 4 and 5. Any question before we proceed further? You can let me know before we can go for the alternate biasing scheme. Right. So, here assume that these devices have W by L ratio, W by L, and here this one is having W by L upon n plus 1 square, where n is an integer. So, this W by L ratio is W by L upon n plus 1 square. If these two 4 and 5 are having W by L, this is W by L upon n plus 1 square. These two are having W by L upon n square. This is also having W by L upon n square. So, this is the biasing condition I have arrived at. So, you have W by L, W by L, W by L upon n square, W by L upon n square, and here you have W by L upon n plus 1 square. And as a result, I have to look at the required. I have to look at the DC gate voltage generated over here with respect to the reference current, and also look at the DC potentials at these 2 points, and figure out that if this is my output branch, this is my branch which is biased with respect to these potentials, what is the minimum allowed potential over here. So, what I am assuming is this 3 and 5 is like my transistor over here, this is 3 and 5, assume that I am trying to generate an appropriate value of gate voltage for biasing transistor stacks of 3, 2 over here. So, this is my output device. I am trying to find an appropriate gate potential for these two devices. Now, if I look at the V overdrive, let me look at the V overdrive of this guy. I can call this, let it be V overdrive. I am enforcing same current in this. So, assume that this branch is also having the same current I ref. That is easy to do. I can just mirror the same current into this and same current over here. So, these two branches are having same current, and if I say that this M4 and M5 is having V overdrive, that is VGS minus VT of M4 and M5 is V overdrive, what should be the V overdrive of this? What is the V overdrive 1? V overdrive 1 is going to be n plus 1 times V overdrive, because ID is V overdrive proportional to V overdrive square and times W by L, and therefore, here you are having n plus 1 square. So, ID is 1 upon 2 mu n COX W by L, which we are changing by factor of n plus 1 square, and then V overdrive square. So, here if I have a ratio of W by L n plus 1 square, the V overdrive will have ratio of n plus 1. Therefore, the V overdrive of 1 is going to be n plus 1 times V overdrive of these devices, and therefore, what is the VG1? VG1 is V overdrive plus VT, because V overdrive is VG S1 minus VT, S is 0, therefore, VG1 is going to be V overdrive 1 plus VT. So, V overdrive 1 plus VT, which is n plus 1 V overdrive plus VT, right, and that is the same gate voltage is applied at the gate of M2 as well as M3. Therefore, now what is the source? If I assume you have the same current flowing through M2, what is the source potential of M2? Vs2, which is going to be Vg2 minus Vgs2, right. So, basically Vg2, which is same as n plus 1 V overdrive plus Vt minus Vgs2. What is Vgs2? Vgs2 is, once again I can write it down as V overdrive 2 plus Vt. What is V overdrive 2? It is having W by L upon n square, it will be n V overdrive, m V overdrive plus Vt, right. Vgs is V overdrive plus Vt for MOSFET, and the Vgs2 is having W by L ratio, which is 1 upon n square, and as a result I can write the Vgs2 as n times V overdrive plus Vt. This is basically same as V overdrive 2 plus Vt2. I am assuming all the Vt's are same. So, I can see that you will get the n V overdrive cancel, Vt cancel, you are just left with V overdrive. So, the source potential of M2, you are forcing it to V overdrive. So, this is now V overdrive, and if I now look at the gate potential of M3 and source potential of M3, now M4 and M5 are having same gate potentials, therefore, it will try to enforce the same current in the M5. VGS of M4 and VGS of M5 is same, it will try to enforce the same current in M5. The gate potential of M3 is same as gate potential of M2, and therefore, it will try to enforce the similar VGS. If M5 is trying to enforce the same current, that will enforce the same VGS for M3 as M2, because their gate potentials are same. M5 is forced to carry the same current as M4, because their gate potentials, gate to source potentials are same, and as a result, you are having the VGS of M3 going to copy the VGS of M2. Therefore, this potential is also going to be V overdrive. That is what we wanted. We wanted that the DC potential at this point should be close to the minimum potential, which is basically V overdrive. So, that is achieved in this scheme. Now, what about the drain potential of M3? So, VD3 is, if we see minimum VD3 min, if I want to say VD3 min, what is the VD3 min I can have under this condition? That is going to be VG3 minus VT. What is VG3? That is same as the VG of this device, M1, which is basically n plus 1 V over drive plus Vt minus Vt. Therefore, you are having n plus 1 V over drive. So, Vd3 min you can have n plus 1 V over drive. So, what should be the n to get the desired minimum output swing that we wanted? 1, so that you have the minimum output potential possible equal to 2 V over drive. So, if I put n equal to 1, I can ensure that the minimum allowed potential at this mirror is 2 V over drive, and that would mean the W by L of these two transistors are same, and here you have just 4 times 1 upon 4 W by L of this transistor. You are enforcing IRF here, and with the help of that you are generating or biasing the gate potentials over here with that current. Is it clear? So, M4 is connected to the drain of M2. Here you do not have any connection. This is not connection, not any connection. So, here this gate are connected. This you can say is a jumper over here, just to make it clear. There is no connection in this line. So, this is the gate of M4 connected directly to the drain of M2. Can you tell me what is the small signal? If I ask you to find out the small signal impedance looking into this node, what is it? If there is a question that find out the small signal impedance looking into this. Why?
Because you are controlling the gate, gate, so it will be GM, it will vary as GM. And the upper one, if you see from the upper one, it will be RO into 1 by GM into RO, into GM, sorry.
Anybody else? I have recorded a wrong response. Anybody else? Why? Yes, tell me. Now, if you put a test voltage over here and you increase that, what is going to happen? VGS is going to change, and therefore the small signal current will be GM VGS. Therefore, you are going to have the current change corresponding to 1 upon GM. So, in this branch, you are going to have impedance very low, 1 upon GM. This branch, same, whatever you just discussed, stacked devices, gate constant, gate at different DC potentials constant. Therefore, this is going to have high impedance GM RO square, and that is going to be applied here in our cascode circuits. This too can be biased with the help of this scheme. So, still have large impedance. This is clear? Any question? So, let us see how we can incorporate this in our cascode amplifier to complete the biasing. So, the NMOS part is more or less there. We can use the biasing scheme that we just discussed. You have this part anyway. So for the NMOS, we have just discussed the biasing scheme where I need to use the cascode device to get the biasing. I can go ahead and have the reference branch being injected with the IRF, the same current coming here with the help of a mirror, and I am producing the gate voltages for these two PMOS. So I can set these two to the required values, and therefore I am going to get minimum allowed potential over here. So the minimum lower side is serving the purpose. I am going to get the minimum allowed VG over here, minimum allowed source potential for this transistor over here. If I follow the convention, I had 2, this is 3, and this is 4, and this is 5. So lower side the scheme takes care of my minimum allowed potential. So this is allowing me to have the DC potential over here close to, let me use this V overdrive, and this is this DC potential is going to be close to V overdrive, and minimum potential over here is going to be 2V overdrive. I am allowed to have minimum potential over here equal to 2V overdrive. That is what we have seen in this particular scheme. On the upper side also, I would like to bias it using a similar scheme. So this 2 PMOS is also carrying similar current, so I can construct another mirror for biasing this PMOS as well. So I can imagine that, okay, means I can have the similar structure for the PMOS. I can have PMOS reference branch, which is basically supplied with the same current IREF. So whenever you're seeing IREF, of course, we can mirror it. We don't need to have so many reference current. One reference current will be there, it will mirror at all these different points. And then I can have a PMOS basically, which is going to be taking the bias voltage here, and another PMOS which is connected over here, and I have to enforce the same IREF over here, and I can possibly use this gate voltage of the PMOS generated over here to possibly bias this. This is one possibility. Can I use this gate voltage to bias this? Two reasons. Means forget about common mode feedback. Suppose we have common mode feedback and everything. Even in that case, suppose output DC potential is controlled. Can we use this to bias this directly, assuming the ratio that we just figured out? Any issue that we can see here? Remember, here when we looked at the overall scheme, we assumed that the current in these 3 branches are almost similar, and therefore we are having certain ratio over here. But if you look at the current here, so I can assume that the current here and here is similar, and as a result the current here I am trying to make it similar, but the current in this device is not same, because current in this device is supplying the current over here and also the current over here. So the current in these 2 PMOS devices, they are not same as the current in this one. So I cannot directly connect it over here and say that my overall biasing condition is met, because the current matching is not satisfied as we used it for the NMOS case. So we need to do something else, and apart from that, another serious issue is the common mode feedback that we also need to account for. So I must make sure that the output common mode level over here, that is close to the desired value, and for that once again I need to apply common mode feedback for the fully differential case, and make sure that we are able to control certain means one of these transistors in the stack, so that the output common mode DC level is achieved. So that will require additional discussion. If if we want to say construct a single-ended version means just like your differential amplifier with diode connected load, it has a single-ended output. So if you want to do that, what modification can be done in the lower part? So rather than taking this as the as a load branch, I can use this diode connected. This is effectively diode connected. As I said, the impedance looking into this one is 1 upon GM, because if you are changing the voltage over here, trying to see what is the impedance over here, changing the voltage over here by a small amount, it changes the VGS of this MOSFET, and therefore the current is going to be GM VGS, and therefore this is acting like a diode connected branch. So I can replace one of these sides by the diode connected branch, and another one remains as it is. So this will be something similar to or analogous to our current mirror load. So if I place this here and keep this as it is, it becomes a cascade kind of current mirror load, right? So that you are having on one side output impedance given by the GM RO square, and on the other side is just 1 upon GM, and then we have we are going to get a functionality which is close to our current mirror load differential amplifier. So, we will discuss that in more detail. That leads to our differential input, but single net output cascode. But if you are going for fully differential cascode, then we need to use a different biasing scheme. We need to first of all bias the load transistors, and at the same time we need to take care of the common mode feedback to stabilize the DC bias point for the overall output. So, let us discuss that in the next module. Before that, any other question related to whatever we have discussed so far? So, biasing is not complete yet. So, related to the both the schemes for the differential input single net output and the fully differential scheme, which is going to require common mode feedback. We are going to discuss both of that, and for the common mode feedback, once again a little bit of discussion on common mode feedback loop stability will be coming into picture. And in this case, it will be relatively simpler because you are having self compensation present in this amplifier. So, once again both the common mode and the differential loops will be satisfied with the same dominant pole. So, here that advantage basically is missing, that you can separate out the differential and common mode loops. So, here because you have a single dominant pole, you will end up compensating both the loops by the help of this dominant pole. But still we need to figure out the common mode feedback configuration, the configuration of the error amplifier, where to apply the input, where to apply the error amplifier output, and so on. So, any questions in whatever related to whatever we have discussed so far? So, starting from the biasing the current mirror and how we are applying it to the bias the bottom two transistors, anything, any part which is not clear, especially in this biasing.
Same biasing not done to the amplifier?
Because it is having a different current. So, this current is not same as the current in this branch. So, here we assume that the current ratios are different. So, you can W by L you can size, and accordingly you can do it. But another factor, that major factor that I told is the common mode feedback. So, you need to take care of the common mode feedback. So, probably you can still use this, you can still bias this PMOS with the help of this, but then you need to have at least one port where the common mode feedback will be coming, and this can be one port over here. So, I would probably like to control this one with the help of common mode feedback. I can apply common mode feedback in other ways also. I can also control these two by common mode feedback and control these two through a current mirror biasing that I did here. So, I can do either way. I can either control both these using common mode feedback, or both these using common mode feedback, or one of these using common mode feedback. All those possibilities are there, but at least one point I have to leave for common mode feedback if I am using a fully differential scheme.
Sir, input pair current and output branch current are same, or they will be different?
They can be different, because important point is that here you need to have a good GM and the RO is over here. So, in order to get good GM or in order to get good noise performance, I can afford to have a larger current here. That is not degrading my RO that significantly. It will affect RO, because if there is a larger current over here, this will degrade the RO of this definitely. But you also have a GM RO square factor over here. Therefore, I can try to reduce the bias current in this stage, but retain a sufficient bias current over here, so that my GM of the first stage is good, W by L as well as bias current is good, so that the GM is large, and at the same time in this stage I can reduce the bias current, so that the RO over here is large.
So, but the top two in PMOS are in the gain calculation, they are
Coming, right. So, overall whatever your GM RO square product is coming, RO R up parallel R down, if you reduce the RO of this, ultimately the GM RO times RO that comes to determine the output impedance, that is going to be affected.
It is from this NMOS and this PMOS.
Both the ROs are contributing, this RO as well as this RO. If you lower both of them, ultimately it will affect your gain also. Noise consideration again becomes important, because noise point of view, will see that just like our earlier case, the noise enforces larger GM at the input device, and the GM of the second stage devices are not important. So, there the GM 1 upon GM ratios over here. GM1 comes in the the overall noise, input referred noise. The GM1 of the input pair comes in the denominator, all others in the numerator. So, we would like to have a larger GM over here as compared to the stage at the output transistors. Any other question? Okay, so we can stop here, and in the next module we can take up the rest of the analysis and complete the DC biasing and common mode feedback.